Hello, everyone, and welcome to the MIT SDM Systems Thinking webinar series. My name is Lois Slavin, and I'm the Communications Director for the MIT System Design and Management program. SDM is a master's program leading to a degree in engineering and management. It's offered jointly by MIT School of Engineering and the Sloan School. If you are interested in learning more, please visit sdm.mit.edu. Speaking of SDM, our speaker today, Ali Kamil, is one of our alums. He will be speaking to you on the topic of logistics that learn a dynamic engine to drive a smarter logistics future. With that, I will hand it over to Ali Kamil.
Thank you, Lois. Hi, everyone. My name is Ali Kamil. Just to give you a quick background, I'm an SDM alum, as Lois mentioned. I graduated a couple of years back with a specialization in how data-driven logistics is transforming the current last-mile logistics future. And in today's presentation, we're gonna cover some of the work that we are doing as part of Y Systems, a company that we founded 2 years ago out of our research at MIT. Spent some time within SDM and the Media Lab, kind of nurturing the idea and then launching it full scale. So we're 2 years old, still young, but learning a lot in the field and seeing how things are changing. So today, next slide. Today, we're just going to go through a quick agenda provide you a little bit of background of what last mile logistics is, what does it entail, and what are the historical solutions, as well as why the solutions are no longer applicable. Primarily because of changing consumer demands and changing consumer experiences. And then we're going to dive into understanding how logistics and companies need to adapt to be able to provide the modern logistics future. Furthermore, we're going to dive into how data, the deluge of data that we've all heard about, how it's transforming logistics future, as well as how companies can learn from it and improve their operations to stay competitive in the field. So a little bit about our company. I mentioned Y Systems came out of MIT 2 years ago, and we have been operating it, providing data-driven, AI-driven logistics models, so companies that deliver goods, services, or are in the business of moving people. With that, we can move to the next slide to just dive into what the last mile entails. So this is the dictionary definition of what the last mile entails. Essentially, is movement of goods, services, or people from a hub or a warehouse to a final destination. And that final destination could be a home, could be a retail store, could be a consumer. So that you have many steps of the supply chain, and many things that we focus on right now in this presentation are going to be pertaining to the last mile, but they can also be applied to the first mile or any operation that requires delivery planning and delivery execution. Okay, and the last mile delivery could be usually in the first mile and intermediate steps. You're taking into account different trucks, different sizes of trucks, but the last mile, as we have seen, most recently, it could include a car, it could include even a motorcycle in some parts of the world. So how that is transforming how companies are providing these capabilities. So we're going to discuss that. So that's just with the focus of last mile. We're going to go to the next slide to see what are traditional solutions that exist. And traditionally, the field has been around for almost 2 to 3 decades. And there have been two basic components. One is fleet management or fleet tracking, and the other is route optimization. So we're going to dive into a little bit of both and describe how historic with that function and how the future has, how we are experiencing these things changing right now. So the next slide, so fleet management, fleet tracking, traditionally, like the first deployment was done in 1993, which is essentially installing a GPS transponder in a truck or any vehicle and monitoring and tracking the vehicle. So that's basic fleet tracking, and from that you can derive many different capabilities from it. You can manage your fleet, you can broker it, you can rent the fleets out and track the vehicles in real time or near real time. Other more recent advances have been on safety front, which is tracking the speed of the driver, hard brakes or sharp turns, any things that the driver takes. So essentially just kind of evaluating where your drivers are, what they're doing, and that's just your basic fleet management operation that exists right now. And as I mentioned, the first deployment was literally this device. Came out of Qualcomm in around 1990 to 1993. And it has been the major mode of operation since almost like it's been a little over 2 decades since then. Next slide is your traditional route optimization. So that is basically you have a number of goods that needs to be delivered. You have a set of vehicles, and you have to have these goods delivered to your target customer. And the next slide, essentially what that entails is, if you go to the next slide, please. So essentially what that entails, back up one more slide, please. Sorry. Yeah. So essentially, route optimization, you have many factors or many constraints that play into building an optimal route. And from your delivery boxes, it could be their weight, their volume, temperature control, any special handling if they're fragile or whatever. These things have to be taken into account, how they're fit into a truck. And then, or your truck, or it could be a vehicle, it could be a motorcycle, it could be a car. So your mode of transport matters. Then based on the mode of transport, you have to consider the vehicle capacity. And that's essentially weight and volume based on what's derived from the boxes or the stuff that you're delivering. And then you have driver availability and driver shifts. And furthermore, you have route restrictions. So it could be a hazmat route, urban route, or rural route, etc. Last mile is the first mile. So those restrictions apply to your delivery drivers and delivery trucks. And finally, for your customer, you have their specific time windows. The time windows, like when the customer shows, when the delivery truck should show up due to delivery. Then you have the service time, which is unloading, loading of delivery. That's taken into account and your priorities. So not all customers are equal. Some customers, if they request a high level of service, they'll be higher priority. So that also plays into it. And combining all these factors, you build a route. And again, there is and that route depends on what are your goals. So if your ultimate goal is to increase driver utilization, so that is one factor. Other factor is customer service, like you want to be on time always. We specify the time window that you give to your customer, or it could also be minimizing fuel costs or minimizing the total cost of your fleet. So that's been the traditional mode of operation for route optimization. And in the next slide, this problem gets increasingly complex, and I'm sure many of you who operate in the industry understand this is the classic traveling salesman problem. So with just 30 stops, your traditional route optimization tools, you're looking at about 4 to 10 to the power 30 route combinations. And your traditional tools will take 2 to 5 minutes to build that route. For 50 stops, it takes 8 to 12 minutes, and 100 stops or more, the time progressively gets higher and higher. And essentially what that means is that companies plan their route at the start of the day or a day before. So if I'm going to do 100 deliveries tomorrow, I'm going to run these route combinations for my drivers and everything tonight, so that if it's more than 500 or 1,000, then it essentially runs for maybe a few hours even. So essentially, when they run this, this software, many of these traditional tools that exist out there right now, the plan essentially looks like this, which looks in the next slide. So that is essentially the sequence of deliveries your driver is going to take in any given day. So he's supposed to go in this sequence of to 1, 2, 3, and 4, and 5, and based on time windows, all these constraints that I mentioned earlier. But then you build the best optimal route, even if you actually, I see a question from Jack Ring, but I will address these questions once I cover the session. So thank you, Jack. So even if so the point is that even if you build the best route possible, let's say you solve the traveling salesman problem, which is an NP-hard problem in its own. What happens is that once you hit the road, the drivers hit the road, then the real-time or unpredictable nature of last mile takes in shape. So in the next slide, you see that there could be issues pertaining to traffic. So the driver may encounter roadblocks or may encounter high traffic when going from one point to another. If you go to the next slide, we live in, at least some of us live in Northeast or some parts of the region where weather plays a has a huge impact in your last mile operations. So during winter months, the driver has to swerve around some snow or maybe snowstorm or something. So that impacts your operations as well. And furthermore, if we move to the next slide, you may have customer cancellations. So customer might not be available, or maybe there might be a delay. There's parking not available, or a driver may not be available for a given day. And if we move to the next slide, there could also be on-demand orders, something that comes up at a given moment in time. And how do you take that into account? You've already built your schedule the day before, but what happens if a last mile, any last minute order comes in? And if you move to the next slide, so the reality is it's what this looks like. So essentially, in reality, your route that you built the day before is no longer valid, because things change, and things actually do change even if you plan for them. So what is the solution around that? And essentially, what that has enabled the industry, if we move to the next slide, please, that even the best plans are going to change. And maybe you make your on-time delivery, like have 1 or 2 on-time deliveries, but the rest will be impacted by how you're conducting your delivery. So you may be late to your deliveries for that. Secondly, you could bypass it by providing a larger time window, saying that to customers that I'll show between 9 a.m. to 1 p.m. And that would enable you to be on time, but that doesn't provide you the level of service. And what we have all experienced, if you move to the next slide, is this experience. The cable guy will tell you that I'll show up between 9 to 5 p.m. And essentially your whole day is gone because you don't know when he's going to show up. So that's how companies, in trying to provide this level of customer service or on-time delivery, they cannot take that the real-time factors and last mile unpredictability into account. So that's just the basic problem of existing solutions that exist in the industry right now, where you plan ahead, you do basic fleet tracking and fleet management, but when things hit the last mile, things do go wrong. So if you move to the next slide. But in the recent times, what we have seen is that consumer experience and consumer demands have changed, and that's primarily because of players in the industry who are providing that level of experience to people. You have Amazon offering 2-hour delivery through Prime Now or other factors. You have ride-sharing companies or the sharing economy where they're providing you the real-time ETA, the accurate ETA for your delivery. So that plays into how consumers are changing, and essentially consumers demanding more and more for their from these companies. So if we move to the next slide. So essentially what, as I mentioned, companies like Uber, companies like Amazon, and many other companies that are operating in the sharing economy, they're providing this sort of real-time view of where your drivers are, where your deliveries are, giving you ETA. So it provides a level of cognitive comfort where you know where your driver is arriving towards you. And this is the ETA, and he's going to be there in that amount of time. And with the press of a button, you can order a car or any sort of delivery in terms of food delivery. So that essentially changed the paradigm of how last mile delivery is operating. So essentially what this means is the logistics and traditional logistics need to adapt to. I'm not saying that Uber is changing how logistics is done, but it has changed how consumers and retailers are thinking about last mile delivery and providing the level of support and level of experience that companies like Amazon are providing to their customers. So in able to do that, we believe that companies need to adapt and logistics needs to adapt because no longer is your future planning is going to be applicable. So if we move to the next slide, so companies used to plan way ahead in advance for a whole month. And the next slide, but now things are moving into like same-day delivery. Next slide would be maybe within an hour, and the next slide is within 15 minutes of your request as well. So this whole and the next slide, you see that essentially the whole on-demand pattern and the industry has enabled logistics to evolve, and there's a need to change, and logistics needs to adapt, and that adaptation will be through understanding your customer, providing accurate ETAs, continuously optimizing, and then also learning from data. So in the next slide, what I mentioned, as I mentioned here, so what we need to provide for the modern logistics future is accurate ETAs, continuous optimization capability, and be data driven so that you can continuously learn from your deliveries and adapt so that you can provide a continuously improving level of service to your customers. Okay, so I'm going to go through each element one by one, and happy to take questions after that. So in terms of accurate ETAs, if you move to the next slide, so providing ETA it's not as simple as calculating a travel time from point A to point B. Calculating ETA requires you to not just understand travel time, but also understand the service time. Service time is when the driver reaches the destination, how long does it actually take me to do the delivery? So if it's a car service, then you don't need to consider that because the customer is going to come to you. But if you're delivering a package or a food item, then you're going to the customer, and that involves understanding where the customer is, how the past deliveries have behaved, and taking that into account as you provide ETAs to your customer. So in the graphic, what you see is you might arrive to a particular doorstep of a building within 3 minutes, but if the customer is on the 12th floor, you have to understand how long it takes to bypass security, how long it takes to get into the elevator, get to the customer door, and then conduct that face-to-face delivery. So that is the historical data that must feed in to your calculation of the ETA. So essentially what Google or anyone else will provide you is essentially a route from on an XY plane. But in cities like Singapore or New York or any of these compact cities which have high rises, then you have to consider the z-axis as well. Essentially, that is a factor that must play into how you build and provide accurate ETA. So essentially, one, you understand if you build an HD map or high definition map of an area, then you can get an idea of how tall a building is, and then based on historical data, you can actually figure out how long your delivery pattern has been for a particular location as well. So that is an important factor to consider when you're doing accurate ETAs. In the next slide, the second part is this whole continuous optimization tool. So as I mentioned in the premise, well, earlier when we talked about is that all static plans are prone to failure. Because you may, even if you solve the TSP, travel and season problem, you will encounter the unpredictability of the last mile. And then how do you consider those uncertainties? And that's one of the questions actually over here as well, so I'll try to address it. So I think that's you have to figure out based on where your drivers are. You have to understand what is the probability of arriving at a particular location, and based on that, is this the right schedule at a given moment in time? And you can take this into account through historical data or run optimization algorithms as well. And historically, optimization algorithms will take a long time to run. So you have to have a bit of a combination of both to prune those results and find out the best options possible, and adjust the schedule as things and circumstances change. To address one of the questions, or actually to illustrate it by example, if we move to the next slide. So let's assume you have a truck that's doing a delivery, has finished delivery at stop 1, going to stop 2, stop 3, stop 4, and 5. Stop 2 and 3 are fine, you'll get there on time, but stop 4 is potentially delayed because of traffic or other problems that might happen in the field. So one way to facilitate it, if you're absolutely sure that if you conduct 2 and if you finish 2 and if you go to 3, if you follow this route that was planned for you the day earlier or in the morning, it's no longer valid. That you will more than likely, there is high likelihood that you will be delayed to number 4. So that's where you bring in your real-time route optimization tool. And in the next slide, that's where you adjust your schedule, your sequence to figure out that, okay, you know what, actually instead of going to 4 to 3, I'm going to go and actually switch the route and go to 3, the potential late delay. And essentially, go to the next slide, please. Essentially, that's what the route essentially evolves to. So it might, so there is obviously a trade-off that happens. This is just a very crude example, but there is a trade-off that happens where if you're doing a real-time route optimization, you might have to maybe travel a few extra miles. But if you value on-time delivery or customer service, then that is some price to pay for certain situations. But it may not be just be a delay. So right now I'm using a delay as an example. But fundamentally, it could also be that that if you are at a particular point, and based on the factors in the future, like how the traffic situations and the weather patterns and everything else looks, the route must change. And at that moment in time, this is the most optimal route for your truck driver to take. So that's why the whole continuous optimization piece must be taken into account as you're building and conducting your last mile deliveries. So this is an example of an essentially within optimization within a driver's schedule. Next slide, we will essentially illustrate the option of cross-route optimization. This is a situation where, again, same situation where your truck 1 is going to go to 2, 3, but it's going to be delayed at 4, and go to 5 after that. So in the next slide, essentially this cross-route optimization would mean that if you're carrying interchangeable goods, interchangeable products, then it's possible to send your second truck to the potentially delayed node, rather than taking a hit or adjusting a schedule for one driver. So that's a second sort of adjustment that must take into account as you're doing your last mile delivery. So this sort of continuous optimization, both inter-driver transfer or schedule adjustment. So factors must be taken into account as you're doing. So that's one way of bypassing the unpredictability of the last mile. So there are going to be delays. That's a fact of life. There's going to be traffic and other obstacles. Your customer is going to be delayed. But how do you react to that? And how do you react in such a way to make it the most optimal sequence at that moment in time? So I covered the accurate ETA and real-time optimization pieces, but the most intriguing aspect where we have devoted a lot of attention and focused primarily on that is how data-driven and machine learning is playing into this field. So in the next slide, I'm going to talk about how the data that we are capturing from deliveries or pickups that are happening in the last mile is enabling us to improve those routes and optimization platform even further. And there are three components of this. First is you have to understand the customer, the customer behavior, how things are happening. Second, you have to understand their drivers. What are the driver preferences? How do they behave? How do they react to certain circumstances? And finally, understanding the deliveries, which is a little more nebulous, but I'll try to cover the deliveries aspect last. Okay. So in the next slide, so essentially this is your customer. You have to understand the time window. So I mentioned that if you have a recurring delivery that happens, customer may on paper say that arrive between 8 to 12 p.m. But based on historical data, you have seen that maybe fast delivery times the driver is actually shown up between 8 to 10. So maybe that is the real time window. Okay, so that is one way where if you have this level of information, if you know that actually the time window by season or by tomorrow or by next month, this is what the time window actually is, and not the one that's actually stated on paper, you can build a better route. Because if I knew that, okay, I had a longer window of conducting a delivery, then I can schedule better. So that's one factor. And then I'm going to come back to the slide after, but in the next slide, second is understanding the customer service time. So understanding how long do actually deliveries take. Because again, on paper, the delivery might take 30 minutes, but you may get in and get out to a delivery. If it's very quick, then it's not 30 minutes, maybe 15 minutes or 20 minutes. In this case, 27.8 minutes, which is not that much of an impact. And it could also be prone to seasonal variations as well. So that is these two are critical factors in how you build and understand your customers. So if you go to the previous slide, actually, in that I mentioned that the time windows are, this is where it is, but essentially based on that, you can actually know when is actually the best time to show up. Because even though, most of the time the driver shows up between 8 to 8:30, but the service time between 9 and 10 is the lowest, meaning that it maybe takes like 40 minutes or 35 minutes to do a delivery between 8 to 9. But after 9, it actually comes down to 20 minutes because maybe that shop owner wants all the deliveries to be conducted in the morning, and everyone shows up between 8 to 9 as it's a full house and it takes a long time to do the delivery. So that kind of learning and interaction will help you figure out your customers and plan effectively. So the next time you're building next time you're building a route, you take into account the actual factors on the ground, not something that was written on paper at the start of the year. So next slide, and then you'll go to the following slide after. Yes, thank you. And then finally, there is something for the demand patterns as well, and this is pertaining to more inventory management, but I think that also plays into how long the delivery might take. Because if you're delivering a lot of material, then it might take longer for the driver to unload and load. So that's also prone to seasonal variations and holidays and other events as well. So that's another way to understand how your customer changes and how their demand and behaviors change over time. So you're not being reactive to it. You can plan proactively based on actual data rather than something that's on paper and hasn't changed in a while. Okay. The next slide. So driver performance. I mean, there's basic tracking that you can do, which is done by basic optimization tools and other software out there. But essentially, using that driver performance, like how effective is your driver? Like, does he or she work best in the morning or in the afternoon? You can use that information to build better schedules, better routes. And essentially what that means is maybe high priority customers, you send your best driver. This is intuitively that happens. Most dispatchers already do that. They already allow it, but this is, again, very intuitive. And if you have a new dispatcher coming in, how would he or she learn to be able to assign the particular driver to that? So that essentially, this is another factor that must play into how you build a schedule and assign the drivers to a particular route, which they're most adept at or most suitable for. And next slide. Another key thing about drivers is also like where do they actually go when they deliver to a customer. So one of the factors is that's critical to consider is where they park, because if they're parking in the back lot, there is a certain time of footsteps required to get to the customer door as well. And similar to what we covered in the accurate ETM model, that is a similar factor that plays into how you build your schedule, how you adjust the routes in real time. So take into account the historical location of where the driver has parked, so that even if that driver goes away or is on vacation and another driver comes on, he or she can figure out, okay, you know what, that's where I parked. And one of the key examples that we have experienced is like in New York City, like parts of Manhattan, which are very, very compact. The drivers would actually go and park to a particular parking spot and then conduct deliveries to 3 stores on foot. So initially, when you're building a route, you would say, oh, you know what, he's going to go to this store, this store, this store, in this order. But that's not really realistic because he's not going to park on the street. So he's going to park at that particular lot and then conduct all those deliveries on foot once he's once he has done the parking. So these are the kind of factors you must play into when you're building a schedule once you are adjusting the routes as well. And finally, one of the next slide is understanding your delivery. So you will have to, based on how the deliveries are conducted in a given city, in a particular geographical location, you can figure out what are the daily delivery patterns, like what are the route preferences by drivers. And I'll come to this in the next slide, but essentially that is one of the factors that must play into building routes and adjusting as well. So in essence, in the next slide, what I'm trying to say is that it has to be an evolving logistics process, and evolving last mile or first mile operation, where you plan, you have to execute, and based on the learnings, you calibrate, and then you plan the next day. So using machine learning models, using data-driven models, you can figure out what is the best operation that fits your needs, fits your customers' needs. And then make sure you're maximizing your utility of the vehicle, maximizing your operations as well. Okay, so I'm going to pause here for a bit. In the next slide, we're talking about what is the next, what's coming up, why this is relevant, because it's cool and it's useful for logistics and operations right now, but it also impacts how where we are going in the future when we have driverless cars and we have Internet of Things and connected vehicles and connected car models. So 3 things where we see where we are building towards and where we see the trends shaping is the scheduler, the Internet of trucks, I guess we can call it, and the driverless vehicle. So I'm going to go through again step by step. So next slide. So where we see is that the whole concept of a scheduler is archaic, and if you have, as I mentioned, if you have enough data for your geographical delivery. There are only a handful of finite delivery schedules or delivery patterns that are useful, that are considered optimal for a set of customers. So if some factors are equal, you don't need to run those high profile logistics operation research algorithms. Just based on data, based on learning algorithms, you can figure out what is the most optimal route. So the whole so we see that there is a scheduler-less future where we're going is just based on your delivery patterns and everything, that you can figure out what is the most optimal sequence at a given moment in time, given all the constraints. So that's one model. Second is next slide. So where we see the whole connected car or connected truck model. So we have been experimenting with this as well. So this is where if your fleets of trucks are able to communicate with each other, you can do faster route optimization. So I mentioned cross-route optimization as one factor. So, but if your trucks are able to communicate with each other, then you can figure out where are the customer delays happening, who is the best person or driver available for the particular delivery. So, so this is not a decision that's going to be made by dispatcher, but something that can be done dynamically in the field. If the trucks are able to talk to each other. Right now, a lot of this is done centralized, but you can decentralize it and have the delivery trucks make those decisions. And essentially what this plays into is that in the next slide where you're going into a driverless future, where for those not familiar with some of the components is you have low-level controllers, the radar, LiDAR, and IMU units. The mid-level control, which is the engine, the artificial perception engine, but the high-level controls is where the route planning and optimization happens. And that's where, in the next slide, that's where we see that this pattern or this sort of a real-time adjustment in modern logistics components are going to have the critical phase where you can adjust routes dynamically. You can do fleet learning models where vehicles can figure out where the roadblock is and automatically balance the network, and that will enable better delivery schedules, shorter time windows, and more predictable last mile logistics. So that's where I'm going to pause, we covered a lot of stuff on a very high level, but essentially where we see a lot of things going and we're building towards, and I'm happy to answer any specific questions as well.
Thank you, Ali. Now is the time to enter any questions that you have for Ali directly into the chat section addressed to everyone. We have a couple already. One from Jack Ring, who asks, in route optimization, how do you consider uncertainties, particularly long haul ones?
Yeah, so that's a great question. So in route optimization, as I mentioned, I think the data-driven models plays a huge role into how we build the route for tomorrow or conduct a real-time route optimization for you. So again, the factors that play into it is historically, what has this route encountered, what has been the speed profile for this particular route, or how long a particular customer takes, like how long does its unloading and loading take. So those are the uncertainties that you have to take into account. And it's no longer, you're not making it, you're making those decisions, you're calculating the probabilistic models based on actual historical data that you have collected for that route, for that particular, for that customer as well.
Great, thank you. From Bruce Tao to everyone, and you may have touched on this already, Ali, perhaps you could elaborate. How do you deal with customer lateness? For example, loading dock is in use.
Yeah, so I think that is, well, actually that's a very specific example, but that's a great question, Bruce. So, yeah, so, I mean, one, you have historical customer delays that happen. And second, customer delays that happen in the field that are happening right now. And one, you have to take into account how much delay is happening. If the loading dock is in use, then the driver can potentially request or can go to another route and come back. So there is that possibility where he can manually say that, you know what, I can't go to a particular customer right now. I'm actually going to go to the next one. So that's one way we tackle this.
Okay.
So, next,
from George Danner, who asks, what role could blockchain technology play in the logistics chain?
That's an interesting question, but I'll be honest, I'm not too familiar with this, and I haven't delved or researched much into this. That's something that is definitely worth, actually on my to-do list. I'll research and see how I can answer this question effectively. Sorry, George, I don't have quite a good answer, so I might come back to this. So, if actually next slide, I have my email. Again, I'm happy to answer questions through that as well.
Thank you, Ali. And actually, I want to reiterate that not only will you be getting links to the recording and the slides, but Ali will be available to answer any further questions that we don't get to today, or just discuss some of the issues with you. Let's see, the next question is from Jack Ring. From an ecological perspective, can you minimize total fuel usage?
Yeah, I mean, that's it's possible. I think from a high level view, I think you could do this. That you could, overall, if we are helping multiple companies, rather than essentially the fuel usage and fuel minimization is the goal. We haven't gotten to that yet. That's definitely a possibility when you're building optimal routes. That's something that's something that definitely can be considered. Yeah.
Mm-hmm. Okay. From Parbat, who says, so using data-driven models, it's obvious that various data can be added to improve service time. But how can we take the abstract factors into account? For example, when I was in Bangalore, often Uber drivers with only local language knowledge were assigned to me, leading to slow service or cancellation of service overall.
So I think it's, I think there are certain factors that, I mean, you have we have encountered this in the field. So actually just to kind of, if we abstract this out a little bit. So you said, I mean, their local knowledge or local language knowledge is a factor. One thing that we have also noticed is, actually we do this, although grudgingly, but essentially what happens is like that your drivers are essentially your salesperson in a lot of these cases. And they have this certain relationship where this driver, Ali, will always go and deliver to a particular customer because they have a relationship. He trusts the customer trusts Ali in that case, and actually has given him the codes for the warehouse and all that. So that is the kind of information, and that the human element is always going to be there. I think what you can do, and what we have, I didn't quite directly touch into this, but you have to understand this institutional knowledge that exists in your drivers, with your drivers, because they know like what are maybe the shortest routes, or where they park, or what are the specific instructions when you arrive for a customer. So I think these factors are still going to exist, and for your example, I think these are going to be definitely. I think it's something that we can only plan so far. That's what I'm trying to say.
Okay. From Richard, have you looked into real-time vehicle inventory using an RFID or other technology into the dynamic route optimization?
Yeah, I mean, real-time vehicle inventories, we have not. We have not, because RFID it's prevalent in the inventory management, but we haven't seen too much of this, at least the vehicles that we operate, or the vehicles that run our software. We don't operate the vehicles. So yeah, we have not, but something to definitely look into.
Okay, from SK, who wants to know, is this an SaaS solution? Would a customer using your solution have to share their fleet data to use your product? And if so, would you tailor the solution specifically to their needs?
First, yes, we are a SaaS solution, software as a service. Yeah, so that's how we offer the capability. We provide a driver solution as well as dispatcher model and as well as other capabilities. So if the customer provides historical fleet data, it helps us understand their operations. So again, you bypass this learning phase. We don't do any customization. I mean, we do maybe some customization, maybe here and there if that's feasible. But as a product offering, we are pretty consistent over there. But what I'm trying to say, if they have historical fleet data available, that helps the learning, that bypasses the learning phase. Because as a new customer comes on, there is that initial learning phase that happens where we don't know where the customer, how long the customers take, what the drivers behave like, or how the delivery patterns for the specific city. Because every specific city, driver, or customer has a different flavor to it, and you have to learn that before you can get the full value over time.
Thank you. Another question from Jack Ring. Does your current algorithm allow driver bidding?
No, right now we don't allow that.
Okay. From Dennis Hose, excuse me, Dennis, if I've mispronounced your name. Can you exclude specific streets, for example, those with potholes? And can you exclude certain routes, say those that include all railroad crossings?
Yeah, so it's possible. I mean, we do take this right now. So it's possible we do this for specific trucks. So if you're a 48-foot truck, you cannot enter a small street. So, and there are designated routes for such trucks. So we already do that. But for specific routes, including potholes and railroad crossings, we haven't run into that yet. But in theory, yes, it's possible. We don't do that yet right now, though.
Okay. I'm sorry, my screen is frozen. I can't get to the next question. Is there one?
I don't see it in everyone's chat window. I can actually read them.
We got one from SK. Is there a guaranteed ROI? What is the true customer value, and how would you measure it?
Is there guaranteed ROI? Is there customer value, and how do we measure it? Well, I mean, this is, again, we'd love to take this offline if there's any specific business-related question. But yeah, I mean, we do measure ROI, like what is the value you're getting, comparing your plan versus actual routes, like how you're planning, how you're conducting your operations right now, and how would it look, how would it look in reality? Like, how would it look in reality, and how does it actually compare to how we would have done it? So that is what we provide and kind of compare the value and proceed to quantify the value proposition as well.
Okay, thank you. Eric, my screen is still frozen. Is there another question?
No, that wraps up the questions for this week.
Okay. I want to thank everyone for attending. Ali, thank you for a fantastic presentation. And Again, you will be sent, everyone that's pre-registered will be sent a link to the recording and the slides, as well as Ali's email address. And you will also get an invitation to our final webinar for this semester, which will be by Dr. David Hartzband, and it will be on healthcare informatics. So we hope you can join us for that. Ali, thank you once again, and good luck with WISE Systems. And to everyone else, thanks for attending.
Thank you, Lois. Thanks, everyone.